Module 5, Investigation 5, Roots and End Behavior of Polynomial Functions. Let f of x equal x plus 1 times x minus 3 squared. Use algebraic methods to find the roots or x-intercepts of f. So if we want the roots, essentially we just have to make our output 0. We want the values when y, or really the output of the function, equals 0. So 0 equals x plus 1 times x minus 3 squared. We really just want to find what values of x make the function 0. You can look in this and see it's x is negative 1 and x equals 3. You could use the zero product property and set each factor equal to 0. You might want to note that this is x plus 1 times x minus 3 times x minus 3. We don't have to set the same factor equal to 0 twice. We'll just get a repeated root. That means the root has a multiplicity of 2. What do the roots of the polynomial function represent? I guess this is just a basic question. Let's see, the roots of a polynomial are the x values for which f of x equals 0. If f of x versus x is graphed, then the roots are the x-intercepts of the graph, where the function crosses the x-axis. Explain why the zeros of a polynomial function occur where each factor is equal to 0. This is a property some of you may have heard about in school, the zero product property. I actually was never familiar with that term until I had graduated from college and started tutoring. Actually, after I'd been tutoring for like 2 years. But let's see, if you have, if you factor a polynomial, meaning you find all the numbers that multiply together to give you that polynomial in terms of x, then in order for the output to be 0, one of the factors must be 0. Really, it's more accurate to say if any of the factors are 0, then the outputs are 0. So we can find the zeros by setting each factor to 0. Without using a calculator, determine the intervals on which the output of the function is positive or negative. Well, I know that the zeros are negative 1 and 3. So let's just think about that for a second. I kind of want to think about a graph here. So I know that at negative 1 I have a 0. So my graph is going to cross right there. And I know at 3 I have a 0. So where's the function positive? I can think about my whole number line being broken up into 3 intervals. What do I mean by that? I mean, like from negative infinity to negative 1, I know my function is either positive or negative because I'm going to cross the axis here, so I have to be either all positive and like come down here like so, or I have to be all negative in this interval and come up here like so. So I can just test that. I can just pick a test value, like let me test the point negative 2. And I can just plug that into the original function. F of negative 2 is, let's see, negative 2 plus 1 times negative 2 minus 3 squared, which is negative 1 times negative 5 squared, which is negative 25. So I know at negative 2, I'm way down here at negative 25. That means that my function is negative this whole interval. It's going to be hard for me to draw this, but it comes up and this is not entirely accurate because it won't go to the right here. It'll actually be moving like this, increasing all the way up to that point, but it's going to be pretty steep. Then what happens here? Like, it could be that we just go right back down to the negative, and then come back up again, or we could go up here and come back up again. So on this interval from negative 1 to positive 3, what happens? Well, let's just pick a test point. Let's pick 0. F of 0 is 0 plus 1, and 0 minus 3 squared, which is 1 times negative 3 squared. 1 times 9 is 9. So at 0, I know that I'm at 9. So I know my function is going to go up here, and then since the next 0 is at 3, it has to come back down. I'm not sure exactly how that is going to happen. Like, it could go up and then go up here a little bit more and then come down. But we know that we're positive from negative 1 to 3. So far we've shown that from negative 1 to 3 we're positive, and from negative infinity to negative 1 we're negative. And then the question is, do we just go right back up here, or do we go down? So what happens from 3 to infinity? Are we positive or negative? We can just plug in, say, 4 into our function. 4 plus 1 times 4 minus 3 squared is 5 times 1 squared, which is 5. That's positive, so the function, once it gets to that 0, goes back up. And I actually knew that because it had a multiplicity of 2. Whenever you have an even multiplicity, like a 2, a square, you're going to have this repeated 0 means it won't cross, it'll actually just touch at that point. So this is a rough sketch of our graph, and we see again that we have positive, the function is positive from 3 to infinity. Then negative from negative infinity to negative 1. Construct a rough sketch of the graph of f. We've already done that, but I guess I can do it again. Here's negative 1. Here is positive 3. We know that we're positive, or actually negative, from negative infinity to negative 1, so our function comes up here, it's negative, and then we're positive the rest of the time. But we have those zeros to take into account. So we're negative, we have to be increasing up to this point, negative 1, but then we're positive, and then we come down and we're positive again. So maybe it looks like that, maybe it looks a little bit different. We could graph it on the calculator to see more accurately how it looks. So looking on my calculator, I can see the graph, but it might be hard for me to sketch this. Not very good at all, but something like this. How do the functions f and h compare? Well, notice there's a 2 here and there's not a 2 here, so all the outputs of h are 2 times the outputs of f. And the book noted one more thing, since the outputs are simply 2 times the outputs of f, and the rate of change is just the change in f over the change in x, or the change in h over the change in x. The rate of change of h is 2 times the rate of change of f at any given point or for any specific interval. Let's see, how do the functions h and k compare, given that h is 2x plus 1 x minus 3 squared and k of x is negative 2x plus 1 x minus 3 squared. So that negative out front just means that all of the outputs of k are opposite of the outputs of h, meaning that the graph of k will be the reflection of h across the x-axis, or the horizontal. Number 5. Let f of x equals x cubed, g of x equals x to the 5th, and h of x equals x squared, j of x equal x to the 8th. Note that a function of the form k of x equals ax to the n, given that a is a real number and n is a positive integer, is called a power function. So note the difference between this one and an exponential function. Notice where the x is. Here the x is the exponent, but here it's not, it's a base. So this is a power function. Let's see, a is a real number, n is a positive integer. Describe how each power function varies. So as x goes to infinity, what happens to f of x? So f of x is x cubed. So just think, as x gets bigger and bigger and bigger and bigger, what happens to x cubed? Well, it gets bigger and bigger and bigger. It goes to infinity. X increases without bound. So if x increases without bound, then f of x increases without bound. Let's look at the next one. G of x is x to the 5th. Same thing. As x increases without bound, g of x increases without bound. It goes to infinity. Yep, all of these go to infinity. And then notice that if x goes to negative infinity, if x decreases without bound, the smaller and smaller x gets, the smaller and smaller x cubed gets, the smaller and smaller x gets, the smaller and smaller x to the 5th gets. That one's different. Let's take a look at those. So we know the first two. These go to negative infinity, those odd power functions. But with x squared, which is h of x, as x goes to negative infinity, what happens to x squared? It goes to positive infinity. You can see x is going to negative infinity, because negative infinity is over here. So as we go that way, the output goes to positive infinity, because we're squaring those negatives. Same thing with x to the 8th. If x gets smaller and smaller and smaller, x to the 8th gets bigger and bigger and bigger. So as x decreases without bound, j of x increases without bound. So this is a positive infinity here and here. What general statements can you make about how the exponent on a power function impacts the behavior of a function? So we notice that if the function is odd, then as x increases without bound, the function's value increases without bound. And if x decreases without if x decreases without bound, likewise the function's value decreases without bound. All of these, the behavior was the same for these odd functions. x goes to infinity, f of x goes to infinity. X goes to infinity, g of x goes to infinity. Or if x goes to negative infinity, f of x goes to negative infinity, x goes to negative infinity, g of x goes to negative infinity. So with odd functions, the behavior of the function is the same as the behavior of x, but with even functions, we saw it was a little bit different. But we observed something a little bit different with even functions. If the function is even, then as x increases without bound, the function's value seems to increase without bound. However, if x decreases without bound, f of x increases without bound. So with x squared and x to the 8th, as x goes to infinity, they both went to infinity, but as x went to negative infinity, they each went to positive infinity because their shape will be more like this. Now note all of these examples had positive leading coefficients, positive 1. If we had negative leading coefficients, we get a little bit different results. Number 6 just says compare f of x equals x cubed plus 4x squared minus 6x minus 12 and g of x equals x cubed. Let's see, I realize that all your numbers might be different from mine. Anyways, how do we compare these? Maybe we should graph them. They're both cubic functions, but if we graph x cubed and we graph x cubed plus 4x squared minus 6x minus 12. Let's see. And this is what I notice. The functions look sort of like this. Here's x cubed, and here's f of x. Notice that in the middle they look totally different. This one has like a relative maximum here, but x cubed just increases forever. But notice as x decreases without bound, like as x goes to negative infinity, both functions decrease without bound. And as x increases without bound, as x goes to positive infinity, both functions increase without bound or go to infinity. Because they're both cubic, they both behave in the same way as we go to infinities, but they behave differently on the local level. For each polynomial function, identify the leading term and describe the functions in behavior. Remember to consider the role of the leading coefficient when determining a function's in behavior. So here the leading term is 9x squared. Now, wait, that's not right. I didn't see that negative 2x to the 4th on the end. You might look in your notes that I gave you guys. Let's see, it says like under polynomial functions, it has the an is called the coefficient of the leading term. And the leading term is where the degree is the greatest. The degree is greatest here at 4. And this is an even degree, but the leading coefficient is negative. There's also a little chart you have here. If the leading term of a polynomial has an even degree and the sign of the leading term is positive, then f of x goes to infinity. As f of x goes to infinity, it seems like there should be another chart that's missing here. But here the leading term is negative. So that means as x increases without bound, so think as x goes to infinity, what's going to happen to negative 2x to the 4th? Well, x to the 4th will also go to infinity, but it's a negative, so it will actually go to negative infinity. F of x will decrease without bound. And as x decreases without bound, what will happen to f of x? So as f of x goes to negative infinity, this term will go to positive infinity, but then it's negative, so f of x will decrease without bound. Essentially what this means is we're just dealing with the end behavior. So regardless of what happens in the middle, at the end behaviors, like the functions are just going to go down. Like we could do all sorts of crazy stuff in here. But we're at the end behavior, the function is going to go down to negative infinity in both cases. Here, this one, we don't have the leading term because the function is not in standard form. We could distribute this x minus 5 times x squared plus x minus 5 times 1, which gives us negative 7 times x cubed minus 5x squared plus x minus 5, or negative 7x cubed plus 35x squared minus 7x plus 35. And so the leading term is negative 7x to the fifth. Now, I know that if it was a positive odd power function, then my end behaviors would look like this. But it's negative, so it's going to flip upside down. Like, I don't know what's going to happen in the middle, but I know that as x goes to negative infinity, as x decreases without bound, g of x will increase without bound, because as x becomes negative, this becomes negative, but then it becomes positive because of the negative 7. And as x increases without bound, g of x will also, will decrease without bound. Answer the following questions given the graph of the function g below. What are the roots of g? Well, I'm just going to name the x values. We can see that's negative 7, negative 2, and 7. Evaluate g of 0. G of 0, the output when x is 0, appears to be about negative 2.5. On what intervals is the function g concave up? Well, remember the concave up is the bowl shape is pointing up. It looks like we have an inflection point where we change concavity about right here at 0. So it looks like from 0 to infinity we're concave up. That's where the rate of change is increasing, and then concave down, it looks like we're concave down from negative infinity all the way to 0. So what's the limit as x goes to infinity of g of x? What does g of x approach as x grows without bound? See that as x goes to infinity, this direction, g goes to infinity. Then what happens as we go to negative infinity? As x decreases without bound this way, we see that the function g of x goes down to negative infinity. Anytime they, as we go in two different directions, the values go in two different directions, it's odd. And then, are there any factors with an even power? I would say yes, because we have these relative maximum points and minimums. That means that it's not just a pure odd function, there's an x squared term in there somewhere. Now actually, this answer would be the answer to this question. Are there any terms with an even power? Some of you guys might have a different question on your worksheet. Are there any factors with even multiplicity? I think maybe. Meaning if we take our polynomial and we somehow factor it, like so, are there any factors with like an even degree here, like something squared? Let's look at our graph for a second. At -7 we cross. That means that x minus -7 is a factor. We just cross, so it has an odd multiplicity. Here at -2 we also cross, so x minus -2 is a factor. And at our other 0, 7, we cross as well. So we don't have any even multiplicities. If we did, we would just touch.